All right, we have one more presentation today. Chris Humann from Halio and previously from Terrestrial Light. He's going to be sharing some information with us about, I think, an incredibly exciting concept of HDR sky imaging as a potential real-time control for facades. So Chris, thanks for joining us.
Thank you, Kevin. It's a pleasure to have been invited to present. Am I okay to present? I think I'm supposed to get a cue from the producer. Okay, great. Okay. My presentation is on a control system we've developed for daylight control of facades for application where controlling electrochromic glass, but it could certainly be used with other daylight responsive facade strategies. I think it's fair to assume that the central tenet of daylight orthodoxy is that daylight is good. Our sense of well-being is improved as well as our productivity. Studies have shown that students perform better in well daylit classrooms, and it's something that we value in our own homes. The problem, however, is that when it comes to the manual control of shading, we as humans are not very good at it, at least after the stimulus that triggered us to lower the blinds has passed. This tends to lead to the shade staying down longer than needed, causing daylight to be squandered, fuse blocked, and more electric lighting being used unnecessarily. To prevent conditions like this shown in this image, automation is seemingly the way forward. While historically automation has mostly been used in high performance and high spec buildings, the benefits of automation are gradually being understood to outweigh the costs. To give some background on this image, this facade was photographed over a course of 3 months, and during that period of time, the shades as shown rarely ever changed from what you're seeing here. For a successful automation system to work, we need a way to read the sky, which is dynamic in the varied amounts of direct and diffuse daylight it offers, which in turn is affected by the temporal and spatial changes of the sun, the clouds, atmospheric effects from such things as smoke, pollution, and turbidity levels. At the very least, a control system needs to discern if the sun is shining. While we can calculate solar geometry quite easily without instrumentation, we need a way of knowing if there is a visible sun or if it's occluded by clouds or by prominent obstructions like buildings on the horizon or nearby. In practice, current state-of-the-art and daylight controls often use rooftop sensors to take global readings of the sky for determining whether the sun is shining or not. The example on the right, this installation is using a pyranometer and capturing or measuring values of global horizontal readings. And they're comparing those readings against a theoretical clear sky for that location. So essentially, they compare the reading to that of the reading of the clear sky. And if the pyranometer reading is a certain amount below this clear sky reading, then they assume that either the sun is blocked or it's an overcast sky. This approach is rather coarse characterization of the sky and doesn't really give us any directional reading of possible sky glare. There are also more sophisticated instruments that offer more nuanced understanding of the sky by measuring the direct and diffuse sky components separately. These often require adjustments if they have moving parts for tracking. The bottom right image, the SPN1 sunshine parameter, is quite interesting as it has no moving parts, but it's cost prohibitive. And again, these efforts or approaches are still very coarse, and they fail to take consideration directional reading of possible sky glare. So in addition to controlling for the sun, we also want to control for bright sky conditions. That can cause visual glare from the diffuse sky component, even in the absence of the direct sun component when it's being shaded by a cloud. Current approaches or strategies for controlling for sky glare often will employ remote window sensors, which create visual clutter, which is antithetical to the architectural intent at most times, are expensive to install and commission, and often the batteries need to be replaced, and sometimes they're just not replaced, and they also create waste. And finally, these are often placed in the wrong location in relation to the occupants they're actually controlling for. During our efforts developing control logic, we determined early on that direct normal illumination, or D&E, offered the best metric for characterizing and controlling for the sun. It tells us in absolute terms if there is sun or if there is not sun, or the sun's being occluded by a cloud. And it also tells us the intensity of what the sun is. D&E is calculated by first measuring the global and then the diffuse values of the sky. The image to the left shows one way of measuring these two values. It uses a shadow disk to shade the diffuse sensor, it's a light core sensor, and then there's an additional sensor that has a clear view of the sky, which is capturing global horizontal illumination. So if you subtract the diffuse value from the global value and then divide by the sine of the solar angle, gives you a correction from horizontal to the angle incidence, or the direct normal value. In the beginning, we were actually using the SPN1 to measure direct normal irradiation, but we wanted something that was less expensive and allowed for better extensibility for future control features. When establishing what kind of sensor to use for our control system, to use as a heart of our control, as the heart of the system, we knew it had to be a sensor that could account for both the sun and sky brightness. Prior work with high dynamic range photography made the HDR process stand out as a viable and even novel approach for capturing and characterizing more detailed and complete reading of the sky. In essence, the process generates a 180-degree luminance map of the sky. These maps are generated by first capturing a bracketed exposure series of low dynamic range photographs and then assembling them into a single image. Once the HDR image is assembled, the image is then calibrated using a measured camera response function that relates the scene brightness to the image's intensities in each of the camera sensor's RGB channels. The response of a typical camera is not linear to scene brightness, so this is an important step to get the accuracy that we were looking for. With the calibration of the HDR image, we can now parse out any pixel or group of pixels in the sky to get a representative reading of the sky brightness in discrete locations or orientations. So generating even a 1200 by 1200 resolution HDR image gives us the equivalent of having 1.4 million center points mapping the sky. One consequence of generating HDR images is that without a neutral density filter to stop down the lens, the sun will saturate the camera sensor before all the sun's photons can be fully captured by the RGB pixels in the camera sensor. This results in the sun's absolute brightness value getting clipped. If you can imagine these camera sensors having little buckets for each RGB channel, the photons fill those buckets up until the photons spill out and we no longer get the value collected of the photons. We can actually use this to our advantage, though, to measure the diffuse horizontal luminance of the sky's diffuse component. To do this accurately, we first block out the contribution of the circumsolar region that falls within a 5-degree subtended angle area around the solar disk. And we do this by masking out this region using a post-process. You can see in the middle image of the HDR image, the black dot or mask in the middle of the image blocking the sun. We then integrate over all the image pixels to get the D&E value. This is the Sky Camera in its productized form. We're using, again, DHE captured from the HDR image, and also we're getting global horizontal illumination measured from an onboard global luminance sensor, which you can see mounted adjacent to the camera body. We can also calculate D&E from these two measures. A few other key features, the camera is powered over Ethernet. It's spaced around the Raspberry Pi compute module ecosystem and uses a custom carrier board. It's also being run on a customized Linux operating system where we're using Python with OpenCV libraries to run the algorithms and the post-processing. There's also an accelerometer for leveling the camera and checking that it is level so we don't clip out the horizon if it's tilted in one biased direction or the other. And the capture frequency is 30 seconds, so we're actually capturing HDR images and processing every 30 seconds. To control for and protect from environmental conditions, the Sky Camera includes several onboard systems, including interior housing and temperature and humidity sensors. housing cap temperature sensor using a thermistor, and then we use that information to trigger a heater that's attached to the housing cap. So if it's a snow condition, then we can heat the cap and melt the snow and allow the snow to accumulate over the camera sensor or the illuminance sensor. There's also a universal ball mount that allows variations of mounting options on any roof structure or appendage. When building and commissioning a Sky Camera, the camera and lens must go through several processes of adjustments and calibrations, one being focusing the lens, which we have a jig that we focus the camera to a target, and then we've got a script that gives us feedback on how blurry the image is. The higher the number, the more in focus that image is, and we get the highest number, we know we've had the lens focus as best we can. The other is this centering the optical axis of the lens over the image sensor. This is important for when we want to locate and parse pixel values at specific orientations and locations based on altitude and azimuth. For this, we use a customized jig and a software routine that gives us real-time feedback on where the optical center is relative to the sensor board. We also need to correct for certain intrinsic flaws that all fisheye lenses have. No fisheye is perfect. We do this by rotating the camera and lens in angular steps on a stepper motor and in relation to a light source of constant output. At each step, we capture an HDR image, and then we combine those images into one image. And then we look at the output of each light source within an image step, and we measure it, and we plot it for calculating a correction function describing light fall off from the center of the lens to the perimeter. We call this the vignetting effect. The graph at top shows you just that. As you go from the center of the lens towards the periphery, the fall off increases quite a bit. Using the same image, we also measure and plot the lens angular distortion. We want the lens to have an equidistant projection where there are the same number of pixels per subtended angle towards the periphery of the lens as there are at the center. If you pay attention to the image on the right, you can see the red dots that are covering the light source. You can see that based on the concentric circle that are drawn, that they're not equidistant from each other. And if you pay attention and look closely as you can, you'll see the change that this correction function has. So now those red dots are more equidistant from each other. As you can see, they follow on the concentric circles. They're equally spaced. The final steps for calibration is we calibrate the camera and the illuminance sensor to a reference light source. In this case, we're using an integrating sphere with a halogen tungsten lamp. We validated the D&E readings of our first prototype from sunrise to sunset over a period of 3 months, comparing the results against a reference shadow disk that we designed and built. We also compared measurements taken simultaneously with the SPN1. For the Sky Camera results, somewhat symmetrical spread on either side of the trend line suggests a change in sky brightness, perhaps, that occurs over the period of time it takes to capture the LDR images before the high dynamic range image is processed. But we're quite pleased with the accuracy we're seeing. We have an error of approximately around 10%, which is pretty good. For the SPN1, the biasness towards higher SPN1 readings might be due to our using a constant luminous efficacy value for converting the radius values from the SPN1 into luminance. We use an average fixed value of 100 lumens per watt, but that value could change up or down depending on time of day, sky conditions, as well as atmospheric conditions. While operational, the Sky Camera performs a daily check at solar noon to test that the camera is correctly aligned with the cardinal directions. We do this by measuring the angle between the calculated sun position and the image sun position. To find the image sun, we first draw a region of interest mask centered around the calculated sun position. We do this to avoid identifying false positives of the sun that might come from reflective surfaces in the scene. Example would be a reflection from a nearby window. So we sort of concentrate the area that we're looking at to a very small 20-degree circle, subtended circle, so that we can cancel out any false reflections. If an angular difference is seen, then the image is rotated to that value that was measured. This is important for when we check for sky glare, so we can identify the glare source's direction and location in the sky in relationship to the building's facade and the associated glass or windows that see the glare source. For bright sky glare, we're controlling this using a metric of calculated vertical eye illuminance at the eye level for occupants near the facade. Once calculated, we convert this value to simplified daylight glare probability. The chart to the right helps explain this a little bit better. So if we measure a vertical eye illuminance at eye level at less than, say, 2,650 lux, the DGP subjective rating is that glare source is imperceptible. For values greater than 2,650 lux, we would start tinting our glass in steps relative to these DGP settings. Or if we were controlling shades, we would just lower them. We can calculate the vertical eye illuminance in near real time, as the brunt of the calculation is done only once as part of the commissioning process. This one-time calculation is done for each window or window groups using radiance in the daylight coefficient method. The daylight coefficient method essentially divides the sky into discrete patches, all with the same uniform brightness. Then the illuminance contribution of each patch to the sensor point, which represents the vertical eye position, is calculated. And once all sky patch contributions are calculated in radiance, the coefficient values corresponding to each sky patch contribution are stored in a matrix on the cloud for later use. On the Sky Camera side, which we call the edge, the most recent HDR sky map is divided into patches by the same number of divisions as we're using daylight coefficient calculation. The average illuminance value of all the pixels within each patch is calculated and then saved in a matrix file in the same order as the coefficient patches were that are stored on the cloud. This file, generated by the Sky Camera, is pushed to the cloud. So when finally we want to compute vertical eye illuminance, and the files from posted to the cloud, the illuminance is calculated by multiplying the luminance values for each of the patches in the sky patch matrix file by the corresponding patches in the daylight coefficient matrix file and summing the results. Given that this final step is purely a matrix math, it's quite fast, given that the brunt of the calculation was computed during the commission process and the results were saved as a matrix file that can be used to establish these vertical eye luminance values. I thought I would conclude with an animation. It's conclusive in that it kind of shows the final product and what the output is. I will play that now. So we have a typical day from sunrise to sunset. This was captured in early October. On the left is the HDR luminance sky map. To the upper right is in orange is the direct normal illumination that's being measured. The blue cyan line is the diffuse horizontal illumination. On the bottom, we're recording the glass tints as they occur relative in response to the D&E values that we're using to control the glass. The purple color is an east-facing glass, while the yellow is a south-facing glass. So you can see as the sky starts to clear, the D&E value goes up and the diffuse value goes down. So now we're approaching sunset in Hayward, California. You can see the D&E value quickly drops. And that is it. Thank you very much.